Hey friends, so hopefully that video gave you a nice, easy introduction to inductive versus deductive reasoning. And that's what we're going to start talking about at the beginning of chapter 2. We're going to it's going to feel like 8th grade logic up until 2.5. And then we're going to switch back to more of a geometry concept. So today we're going to look directly at just inductive reasoning. Okay, do you understand inductive reasoning? And like the video showed us, inductive reasoning is the process of coming up to a general conclusion by finding a pattern. Okay, we're using a pattern. The conjecture is our conclusion that we reach. This is the pattern things that you did in elementary school. Not colored, not colored, colored. Not colored, not colored, colored when you are looking at shapes, right? So not colored, colored in, and they said not colored, finish the pattern. This is inductive reasoning. You're looking at what has happened to conclude what is going to happen. So let's look at example 1. Make a conjecture describing the pattern of each series of examples. Then find the next 2 items in each series. Okay, so look at example A. Classes begin at 8:15, 9:05, 9:55, and then what do you think the next class begins at? Well, if we look at each class period, it looks like each class period is 50 minutes long, and each class starts 50 minutes after the previous class. So 50 minutes from 9:55 would be 10:45 and then 11:35. So this would be like 10:45, 45. Well, it's not going to want to do it. And then 11:35. Okay? Because each class starts 50 minutes from the previous start time. Looking at example B, we're looking at dot patterns. Okay, a lot of you guys see this as a pattern, right? We've got 1 here, then we've got 1 plus 2, then we've got 1 plus 2 plus 3, then we have 1 plus 2 plus 3 plus 4. So this next one would probably look like 1 plus 2 plus 3 plus 4 plus 5. Okay, and then the one after that would be adding 1 more row at the bottom of, I didn't do the 5, did I? Oh, I'm having it. Look at that, that's crazy. Go back. 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and then the last one will be 1, 2, 3, 4, 5, 6. I just wasn't coloring enough dots. All right. So those are pretty easy. Looking at C, we have to think just a little bit more going into C. So if we look at what we've got here in our picture, we've got a nice circle triangle with a solid line, square circle with a dotted line, triangle square with a solid line. What is this asking us to do? Well, first of all, let's look at the line in the box. So let's concentrate just on the diagonal line that's in the box. So if I'm going to draw the next one, here's my box. Oh, I went out of the picture. Would my next line be solid or dotted? So if I'm looking here, I've got, all right, solid, dotted, solid. All right, so my next line would probably be dotted. Okay, so that's my first conjecture, whereas the box after that would be a solid line. Okay? Now, the 3 figures that kind of rotate being in the frame is a circle, square, and a triangle. And it kind of looks like, if you imagine it as this, kind of it just pushes its way up this direction and goes around in a circle. So the circle pushes its way up, square comes in, square pushes its way up, triangle comes in. So in this next one, triangle would push its way up, and following behind triangle is circle. And then circle would be pushed up. And following behind circle would be square. Okay, this is just kind of a pattern, and hopefully you're able to see this. This is something that a lot of students are pretty adept at seeing at this point in their schooling. So example number 2 is asking us to make a conjecture describing each instance. Okay, so what it wants us to do is give an example. Give a couple examples. All right, so let's look at example A of 2. The product of an odd and an even integer. All it wants to do is give us an example. There is an infinite number of examples we could give here. The product, first of all, what is product? Hopefully you remember, product is multiplication. So the product of an odd, let's say 3, and an even number, 6. And 3 times 6 is 18. Okay? I could have given other ones. I could have given things with negative numbers. So I could have said negative 7 times 2. That would have been fine because that is the product of an odd number, negative 7, and an even number, 2. Now part B is asking us to make a conjecture describing the sum of the measures of the angles in a triangle. Well, we know that a triangle is composed of 3 angles, and those 3 angles have to add up to 180 degrees. So I could make any conjecture I want. I could do a right triangle, which this one kind of looks like a right triangle, right? And this would be 90 degrees. And I could say this is 30 degrees, and this is 60 degrees. That would work. I could give a kind of scalene triangle right here and have 54, that's a 54, 61, and 65. So that would work. So again, there's quite a few variations on this. Okay, you could make it go a couple of different ways. All right, a conjecture can be proven false by giving a counterexample. Okay? A counterexample is an instant in which your conjecture is false. Okay? So whatever you're saying, whatever you give as a counterexample, disproves the conjecture. Okay? So let's look at example number 3. Example number 3 says, after examining the listed products, Jennifer concluded that every multiple of 3 is odd. Give a counterexample to show this conjecture is false. So what she is saying is that every time you multiply anything by 3, the answer is always going to be an odd number. Well, hopefully you go really simple and you say, oh, hold on, Jennifer. 3 times 2 is 6. 6 is even. There's your counterexample. So your conjecture, which says every multiple of 3 is odd, is big, fat, false. Okay? So this proved her conjecture false. All right? You could give another 3 times 4, right? It's 12. 3 times 8, 24. So we could talk more about that, but we'll just move on. We'll let Jennifer, we'll figure that out for another date. All right, so let's look at example 4. Joseph. Joseph claims that this function here, I won't read it for sake of crazy, can be used to find the sum of the first n squares. Give a counterexample to show this conjecture is false. Okay, so what it's asking you to do is if you think back to algebra and you think to a t-table, remember those t-tables? And we said this would be our, our domain and our range. This is n, and this over here would be the f of n, okay, or the y. So in the middle is the f of n is equal to 1/2 n cubed minus 1/2 n squared plus 2n minus 1. All right, so what it's asking right here and what it's saying is that if we plug n in, if we chose 1 as the variable, okay, we could plug that in right here and it would be 1/2 of 1 cubed minus 1/2 of 1 squared plus 2 times 1 minus 1. If we do all of this math right here, this is equal to the number 1. And what Joseph is claiming is that this 1 that we found right here is equal to the n squared. Well, n squared is equal to 1. So I don't know. Maybe Joseph, maybe you're on track, Joseph, but the only way we can figure it out is if we keep going. So the next n we would choose would be 2, right? So this would be equal to 1/2 of 2 cubed minus 1/2 of 2 squared plus 2 times 2 minus 1. If we did all this math for Joseph, this would be equal to 5. Hopefully you know how to use your calculator and plug it in there. Okay, that would be equal to 5. And now what Joseph's conjecture said, this formula is the sum of the first n squareds. So what Joseph is saying is that this 1 squared plus 2 squared should also equal 5. And it does, because 1 squared is 1, 2 squared is 4, 1 plus 4 is 5. So it works. So far, Joseph, you're seeming pretty good. I'm going to skip down. I'm going to skip 3, and I'm going to move to 4. And it's just because of the sake of space on my screen. If I plugged 4 in, this becomes 1/2 of 4 cubed minus 1/2 of 4 squared plus 2 times 4 minus 1. Now, again, if I used my calculator and did that math, that gives me the number 31. Okay, that's the formula. Now, again, Joseph said that what that looks like is 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, let's look a little closer at that math, okay? 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. Oh, if we use our brain and we add this up, that gives me 20 plus 9 is 29 plus 1 is 30. Hold on, Joseph. These two are not the same. This example, this one example right here, has proved Joseph's conjecture false. So we can say false, Joseph. Okay? All right. So let's look at this. A fallacy. Again, you're going to feel like you're back in 8th grade logic, but that's okay. We just need to do a couple of definitions here. A fallacy is where you have a deception, where we are deceiving or creating a deception. A hasty generalization is a common fallacy related to inductive reasonings. Don't draw conclusions based on insufficient evidence or non-representative examples. You'll hear me say this a lot. Don't trust a picture, okay? A lot of students will say, well, they look like parallel lines. Don't trust the picture. Unless it tells you they're parallel lines, don't trust it. Don't trust the picture. Goldbach's conjecture says every even integer greater than 2 can be expressed as a sum of two prime numbers. This conjecture is one of the oldest unsolved problems in mathematics, and if we get around to it this semester, hopefully we can dig into this conjecture. It's a really fascinating study on how mathematicians have tried to solve this problem over and over and over, and we just can't. Okay, so every even integer greater than 2 can be expressed as the sum of two prime numbers. And we can talk about that later on when we talk about some interesting number patterns. All right, so hopefully you're filling out your TRF today. If one of these problems gave you a little issues, let me know tomorrow when we do our bell ringers. Tomorrow in class we are going to work on 1 through 31 odd.